Okay, so in this video, what we are going to do is study the fundamental theorem of calculus. The fundamental theorem of calculus is essentially what establishes the relationship between the integral and the derivative, right? It establishes some sort of a inverse relationship between these two operations. So that is what is called the fundamental theorem of calculus. We will essentially study two statements of the fundamental theorem of calculus. These are not these statements don't imply one another. They are distinct statements. One of them deals with the integral of the derivative, and the other deals with the derivative of the integral in some sense. Okay, so the first of these results we are going to call that FTC One, or fundamental theorem of calculus 1, and the statement is as follows. Right? So suppose that you have g, which is a continuous function on AB, which is differentiable in such a way that g prime is integrable. Okay, so which means you have a function which is differentiable and has an integrable derivative, right? If that's the case, then the integral of g prime from a to b is simply g of b minus g of a. Okay, so that's the so if you look at the left hand side here, you are basically looking at the integral of the derivative of g. Okay, now one thing that you might notice about the statement is that it assumes that g prime or rather g is differentiable on the open interval AB. In other words, g prime may only be well defined on the open interval AB, and yet you hypothesize that g prime is integrable on the closed interval AB, right? So then you might ask, how is it that that's allowed? Well, then the convention here is that we say that if you have a function h which is defined on the open interval AB, okay, we say that this is integrable on the closed interval AB if some extension of h over the closed interval is integrable. If some extension AB is integrable, right? This is what I mean by saying that g prime, which may only be well defined on the open interval AB, is integrable on the closed interval AB, right? That means that some extension of g prime should be integrable on the closed interval AB. And another thing to note, if some extension is integrable, then any extension is integrable. If some extension of h is integrable, right? Why? Because if you have an extension of h which is integrable on the closed interval AB, then any other extension can differ from this integrable function at most the endpoints AB. So which means if you can find one extension that's integrable, then it turns out that any extension is integrable, and so on. Okay, so with this language, I hope the statement of FTC 1 is clear. Namely, g is continuous on the closed interval, differentiable on the open interval AB in such a manner that g prime, which is the derivative of g, should be integrable on AB. If that's the case, then the integral of g prime over the interval a to b is in fact g of b minus g of a. Okay, so that's your statement of FTC 1. So now let's go through the proof. Okay, so pick any partition P on AB. Okay, now by the mean value theorem, in each subinterval of this form tk minus 1 through tk, there exists some xk such that the following is true: g of tk minus g of tk minus 1 is equal to g prime xk times tk minus 1. So recall that this is in fact the statement of the mean value theorem, and verify that the hypotheses of the mean value theorem do indeed apply over the subinterval from tk minus 1 to tk. Okay, so therefore you know that the difference between the g values at tk and tk minus 1 can be related to the length of the interval into the value of the derivative at some point xk within the subinterval from tk minus 1 through tk. Okay, now we say the following, right? If you look at the lower sum of g prime over the partition P, this is in fact going to be less than or equal to summation from 1 through n g prime xk times tk minus 1. Right? Why? Because in the lower sum you would have to actually write the infimum of g prime over the subinterval tk minus 1 through tk. What you have replaced it is by the value at some point xk. So which means the lower sum is going to be a lower bound, and similarly the upper sum is going to be an upper bound on the same summation. That is u of g prime comma p, because in u of g prime comma p you would be having the supremum of g prime over the subintervals, right? So therefore we have sandwiched this summation between the upper sum and the lower sum at partition P. Okay, but from the previous equation that we have written here, note that the summation of g prime xk into tk minus 1 is in fact simply g of b minus g of a. So that means that L of g prime p is less than equal to g of b minus g of a, which is less than equal to u of g prime comma p. Right? So for any partition P, we have said that the lower sum and the upper sum are sandwiched between sandwiched between g of b minus g of a. Okay, this in turn implies, given that g prime is integrable, that g of b minus g of a must also be the value of the integral. Since g prime is integrable, right, that means that as p becomes finer and finer, L of g prime p will approach the value of the integral. U of g prime p should also approach the value of the integral from above, right? And so if there is a number which always lies between these two, that must in fact be the value of the integral. So since g prime is integrable, g of b minus g of a must in fact be equal to the integral of g prime from a to b, right? And that completes the proof of the fundamental theorem of calculus 1. Okay, so if you think about it, the proof is essentially an elementary application of the mean value theorem, right? That's all it takes to really prove the first fundamental theorem of calculus. Okay, now we move on. Before we move on to the second fundamental theorem of calculus, what we are going to do is construct a corollary of Ftc One, which is in fact of considerable value in its own right, and that is going to be the theorem on integration by paths. Okay, so the statement is as follows: if u, v are continuous on AB, differentiable on the open interval AB, such that u prime and v prime are integrable on AB, then the following is true. Look at the integral of u v prime from a to b plus the integral of u prime v from ab. This is in fact equal to u of b v of b minus u of a, v of a. Okay, so u and v are continuous on the closed interval ab, differentiable on the open interval, such that the derivatives u prime and v prime are in fact integrable over closed interval ab. Interpretation of this again being what we said before, right? Namely that some extension of u prime v prime are in fact integrable on the closed interval ab. In that case, the integral of uv prime plus the integral of u prime v is equal to if you look at the product function u into v, it's the evaluation of the product function at b minus the evaluation of the product function at a. So this is perhaps not very clear. This is v of b. Yeah. Okay, so that's your statement of the integration by parts result. The proof is in fact going to be a somewhat trivial application of Ftc One. Okay, so let g be the function u times v. Okay, in this case we know that g prime would in fact be u v prime plus u prime v from the product rule of differentiation. Now it can be shown to apply Ftc One, you have to argue that g prime is in fact integrable. Right? How is that? Well, if you look at g prime, it actually involves terms of the form u into v prime. So you are multiplying two integrable functions, because we know that u is integrable, we know as v prime is integrable. Similarly, I know that u prime is integrable and I know that v is integrable. So the conclusion that g prime is integrable follows from the more general result that the product of integrable functions is integrable, right? Which I'm going to actually post as an exercise problem for you guys. So this follows from the fact that the product of integrable functions is integrable. Right, so I invite you to try and prove this yourself right away. And how do you, I mean, as a hint on how one would go about doing this, one possibility would be to say that if f is integrable, show that f square is integrable. Right? If you can prove that if f is integrable, f square is integrable, then that say something like fg, which is a product, is integrable, actually follows quite straightforwardly, because then you can use the fact that f times g is in fact a quarter of g plus f the whole square minus g minus f the whole square. Right? So essentially what I'm trying to say is that if you can prove that the square of an integrable function is integrable, it then also follows that the product of two integrable functions is integrable. Okay, all of this is going to be exercise. So assuming that that exercise, the statement of that exercise holds, it therefore follows that g prime is in fact integrable. And once g prime is integrable, then you can just apply your FTC, because by Ftc One, the integral of g prime from a to b, which is in fact, well, integral of u v prime plus integral of u prime v, must in fact be g of b minus g of a, right, which is u of b times v of b minus u of a times v of a. Right? That completes the proof. So the claim here is that subject to this exercise, that the product of integrable functions is integrable, the integration by parts rule, which we are all familiar with, is in fact a trivial consequence of Ftc One. Okay, so yeah, before we move further, maybe it's worth doing one example applying the integration by parts statement that we have just written, suppose I wanted to evaluate the following integral. So integral from 0 to pi x cos x. Okay, now how do I go about doing this? Well, I could apply the integration by parts result that was written earlier by interpreting x to be u and cos x to be v prime. Okay, if I do that, then we know that integral from 0 to pi of x cos x, right? This is the integral of u v prime plus the integral of u prime v. U prime is 1, mind you, and v is sine x, right? Because the derivative of sine x is what is cos x. From 0 to pi is in fact, uv evaluated at pi minus uv evaluated at 0. So uv would be x into sine x. So pi into sine pi minus 0 into sine 0. Okay, now again, I know how to evaluate the right hand side. I know how to evaluate this term because just the integral of sine. Then one round of algebra which I'm going to leave to you will in fact show that the integral from 0 to pi of x cos x is in fact equal to -2. Okay, so at this point what I'm going to do is stop, and in the next video we will basically cover the second fundamental theorem of calculus.